Stanford University.
Let's talk more about conformal mappings. These are very interesting in their own right. They are widely applicable to all kinds of mathematical physics problems. The most direct is electrostatics problems in 2 dimensions. There are problems in theoretical physics which are mathematically equivalent to the electrostatic problem in 2 dimensions. When I say, incidentally, the electrostatic problem in 2 dimensions, I don't mean that you have particles, charges moving in 2 dimensions which interact with each other with 3-dimensional Coulomb forces. I mean particles which move around, electric charges which interact with each other with mathematical 2-dimensional Coulomb forces. Does anybody know what the Coulomb force between particles is in 2 dimensions?
1 over r?
1 over r, not 1 over r squared. How about the potential energy between a pair of particles?
You'd have to integrate.
Logarithm. Logarithm, because the derivative of logarithm is 1 over r. So in a world, a literal world, where the lines of flux can't escape out into the 3rd dimension, which are really forced to lie in the plane, in such a world, electrostatics problems would have Coulomb forces, which were 1 over r instead of 1 over r squared, and the equations of electrostatics would be 2-dimensional versions of the corresponding equations in 3 dimensions. What are the equations of electrostatics? Let's just write them down on the blackboard for a moment. What do you describe an electrostatics problem by? You describe it, of course, by an electric field. But there's something simpler than the electric field. What is it? Electric field is a vector. What's simpler than a vector? Well, charges, but a scalar. A scalar. The electrostatic potential, which is sometimes, it goes under different names, but let's call it phi. What's the connection between phi and the electric field? The gradient of phi is the electric field. All right, so the gradient of phi is the electric field. And what's the equation for the electric field in electrostatics? Divergence of the electric field is the charge density, right? Charge density on the right-hand side, call it rho. And we can rewrite that in terms of phi by writing that it's, I'll write this out in detail in a moment, del squared phi equals rho. Del dot phi is E, del dot E equals rho, so del squared phi. And what does del squared phi mean? If we're in a 2-dimensional world, literally a 2-dimensional world, let's say with coordinates little x and little y, then what is del squared? Del squared is the 2nd derivative of phi with respect to x squared plus the 2nd derivative of phi with respect to y squared. And that on the right-hand side is rho. If there's charge density, it's not 0, but if in places where there is no charge density, in places where there is no charge density, it's just 0. You remember last time, I think it was last time, we talked about this equation and its invariances. Conformal invariance. This equation is invariant or unchanged by any change in the xy coordinates, any transformation to new coordinates, xy coordinates, such that that transformation is conformal. Conformal means angle preserving. In other words, that when you make a transformation, when you the angles, well, let's just say the angles in the new coordinate system are perpendicular, and that angles in the new coordinates are exactly the same. Angles between curves in new coordinates are the same as between the old coordinates. Conformal mappings. Those are conformal mappings. And they are the kind of mappings that cartographers use in order to preserve the shapes and the angles on a map, although they cannot, in general, preserve the sizes of things. Okay, so that's an example of a place where conformal mappings occur. Other places, fluid flow in 2 dimensions. These are also equations of fluid flow. All kinds of problems, at least approximately, are described by Laplace's equation.
When the Laplacian is 0, you have a standing wave?
No, this is not wave equations. These are not wave equations because they have a plus sign there. These are electrostatic equations, and they don't describe wave motion. You have to add, if you want waves, you got to add in the t-dependence. So there's a reason why we call electrostatics electrostatics, because nothing is moving, right, including the waves.
Then you have, is there a curl in 2 dimensions also?
There is a curl in 2 dimensions. It's a good question. Let's come back to it when, well, yes, there is a curl in 2 dimensions. The curl in 2 dimensions is if you have a field like E, which has 2 components, let's say E sub x and E sub y, the curl only has 1 component. In a 2-dimensional world, the curl has 1 component, and it is derivative of Ex with respect to y minus the derivative of Ey with respect to x. That's the component of the curl. You could think of it as the component of the curl in the direction perpendicular to the blackboard. But you know, you can be in 2-dimensional worlds where there is no direction perpendicular to the blackboard. So just think of it as the curl. The curl becomes a 1-component object in kind of scalar in 2 dimensions. It's only in 3 dimensions that the curl is a vector. In higher dimensions, it's something else. It's a 2-form, but okay. Let's talk a little bit more about conformal mappings. As I said, they are very interesting. What they allow you to do, incidentally, is from the solution of a problem, an electrostatics problem, for example, on some kind of space, some sort of space, perhaps with boundaries, with some boundary conditions, you can derive an infinite number of other solutions with problems with other boundary conditions, just by mapping the surface and taking the solution with you and mapping the solution to a new solution by conformal mapping. So as I say, there's all sorts of applications of conformal mapping to electrostatics problems. We're going to come back to electrostatics tonight at some point, but let's talk more about conformal mappings. A conformal mapping is a mapping of the plane, the xy plane, or the plane to itself. So here's a Cartesian plane described by x and y, and let's use a complex coordinate, z equals x plus iy. A usual complex plane or usual complex notation representing the plane. Now, we want to do a mapping of the plane to itself, or a coordinate transformation of the plane. Here's the w plane over here. W is equal to u plus iv. This is u, and this is v. Incidentally, for obvious reasons, x is called the real part of z, and y is called the imaginary part. Likewise for u and v. And a mapping from the x-plane to the w-plane is just a rule given any point in x and y, assign to it a unique, and let's assume the mappings are 1-to-1. In other words, for every point on the x-plane, there is a unique point on the w-plane, and likewise, for each point in the w-plane, there is a unique point in the x-plane. That means any point can, Did I say it wrong? No, you know what I meant. For any point on the w-plane, there's a unique point in the z-plane, and for any point in the z-plane, there's a unique blah, 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 blah. Okay. This means you can take any point and represent it either by coordinates x and y or by coordinates u and v, and in that sense it's just a coordinate transformation. U and v are functions of x and y, or you can say that w is a function of z. So let's think of it, and vice versa, but for today I'm going to think of w as a function of z. Given a point z on the complex plane, it uniquely picks out a point w. These are complex functions. Both the argument of the function z and the function itself w are complex numbers. All right. Now, there is a calculus of complex functions like this, called complex variable theory, and let's just spend a few moments on it. There's both an integral and a differential calculus, but we're going to concentrate on the differential calculus. Given a function w, we can try to define a derivative, w of z. We can try to define a unique derivative, and here's the way we would do it. Start at a point z, and at every point z, that corresponds to some point over here, w. Let's move the point z a little bit to z plus delta z. Here's z, and move the point to z plus delta z. When you do so, w will move to w plus delta w. Here's w. Here's w plus delta w. Okay. What is the derivative of w with respect to z at the point z? Well, the answer is obvious. It is delta w divided by delta z, in the limit that delta z goes to 0. Usual logic of what a derivative is, it's the difference between the function at neighboring points divided by the difference between the coordinates at neighboring points. There's only one problem, something new. Right? You can approach the point z from any direction. And it's not at all clear that in general, even if the function is nice and continuous and has all sorts of good continuity properties, it's not obvious that when you calculate the ratio delta w by delta z, and then shrink the size of this, that the answer will be independent of which direction you're coming in from. You might get one answer if you come in from here. You might get another answer if you come in from here. You might get another answer if you come in from here. So the question then is, what is the condition? If you want to have a nice mathematical framework for complex functions, and you want to have the notion of a unique derivative, maybe there is no good definition of the derivative, but let's see what the conditions are that the derivative, the limit of delta w over delta z, exists and is independent of which direction you come in from. Now I'm going to show you a sufficient condition. You can go home and prove it's a necessary condition. It is a necessary condition. And it's almost as easy to prove as what we will do, but I'll leave it for you for homework. To prove, what I'm going to do is work out the necessary condition by asking that the ratio, delta w over delta z, is the same if you come in from the x-axis, along the x-axis, or if you come in along the y-axis. In other words, if your delta z is along the x-axis or along the y-axis, that you get the same answer. It is then not hard to prove that if that's satisfied, that no matter what direction you come in from, you get the same answer. So I'll do the simple thing. You can do the slightly more complicated. It's only a little bit of algebra, but I don't like doing too much algebra on the blackboard. Okay, let's calculate delta w by delta z. Now, first of all, what is delta w? W is u plus iv. why don't we, let's not be babies. Let's call it dw by dz. Whenever I teach pre-meds, I'm not allowed to use calculus. And so every time there's a derivative, we call it delta w by delta z or whatever, and then we're not officially using calculus, and that's legal. But then I secretly tell them, you realize that's a derivative. And they say, yeah, we know. But I'm always afraid if I use it that they'll tell the ombudsman that I'm using calculus in class. Okay, so the change in w divided by the change of z. And what, of course, is that? That's equal to the derivative of, or the change, the small change in u plus the small I times the small change in v as you go from here to here. Derivative, or the differential of u plus iv divided by the differential of x plus I dy. Okay, that's very straightforward. Now let's calculate it if I come in along the x-axis. If I come in along the x-axis, then dy is equal to 0. Okay? dy is equal to 0 if I come in along the x-axis. And so this must equal, coming in along the x-axis, it must equal du by dx plus I dv by dx. Since we're keeping y fixed and not varying y, this is the same as the partial derivative of u with respect to x plus I times the partial derivative of v with respect to x. Oops, with respect to x. Okay, is that clear? Good. Now let's come in along the y-axis. If I come in along the y-axis, dx is equal to 0, dy is not 0, and the partial derivatives are partial derivatives with respect to y. So let's see what that has to equal. If, under the presumption that dw by dz doesn't depend on which direction you come in from. Okay, so let's see what we have to have. Then we have to have 1 over I. The 1 over I comes from the I. The x is going to be 0. There's a 1 over I from the 1 over I multiplying dy. And then we'll have partial of u with respect to y. And then I over I will just give you derivative of v with respect to y. U and v are real. I neglected to say so. It may have been obvious. U and v are real. It's w which is complex. X and y are real. Z is complex. It's at least a necessary condition. It happens to be sufficient also, but it's at least a necessary condition that this expression equals this expression. Necessary for what? Necessary that the derivative not depend on which direction you're coming in from. Okay? Now, so let's take the real and imaginary part. Whenever you have an equation that involves real and imaginary parts, it really stands for two equations, equating the real part and equating the imaginary part. So let's start with the real part. Here's a real part. That's got to equal this. Du by dx must equal dv by dy. And what about the other one? The other one says, let's see, that's the real part. Here's the imaginary part. Let's put it over here. I dv by dx equals 1 over I du by dy. The I dv by dx has to be 1 over I du by dy. That's equating the imaginary parts. Let's multiply both sides by I and use the fact that I squared is minus 1. So we get two equations. There are two. They're not the same, incidentally. Look at them. One says du by dx equals dv by dy, and the other says du by dy equals dv by dx. No, minus dv by dx. One of them has a minus sign, the other doesn't. If these equations are not true, then the derivative doesn't exist in a meaningful and unique way. If they are both true, then the function w of z has a derivative, and the derivative is well defined, and the function is called analytic, just a name. When a function, a complex function of a complex variable has a unique derivative from every direction, it's called analytic at that point. If it's analytic everywheres, then it's called entire, all sorts of names, meromorphic, holomorphic. I never understood what they meant.
Holomorphic is analytic.
Now, meromorphic allows poles and,
Holomorphic is the same as analytic.
yeah, holomorphic is the same as analytic. I think that's right, I don't remember. There's fancy names for everything. I've learned recently that a mapping which takes a point to a point is called a bijection or something.
Well, we do diffeomorphisms and all.
Yeah. These coordinate transformations are diffeomorphisms. Right, but all they are is coordinate transformations. Nice smooth ones. Okay, so we have now the necessary and sufficient conditions for a function to be analytic every place where these are satisfied. Now let's look at these equations a little more, just for fun. See what they say. They're coupled equations for u and v. Can we uncouple them and write an equation just for u and an equation just for v? Yes, we can. Here's the trick. Let's differentiate this equation with respect to x. That gives us d second u by dx squared, the second partial derivative with respect to x, and that's equal to dv, that's equal to the second derivative of v with respect to x with respect to y, the mixed partial derivative with respect to x and y. Let's differentiate this one with respect to y. That's d second u by dy squared. That's equal to minus d second v by dx by dy. That's the same as that except for a minus sign, so it follows that we can eliminate it, and one equation is d second u by dx squared minus, sorry, is plus, this is u. Yeah, no, we have, just add them. Add them, and the right-hand side will go away. Well, that's a familiar equation. That's just Laplace's equation in 2 dimensions. So, a necessary condition.
Well, something looks a little like your curl equation, too.
It does.
So it's some
It does.
sort of curl free.
Well,
That's,
this one,
yeah,
yeah.
that sort of is it the derivative is curl free in some sense.
yeah. One of them is curl and the other is divergence, depending on which way you define the components. Yeah, if you think of u and v as components of a vector, actually you have to think of u and minus v as the components of a vector. Then what it says is that the curl and the divergence of the vector vanishes. Okay, so that's this equation, and if you do exactly the same thing, we differentiate this one now, instead of with respect to x, we differentiate it with respect to y, and differentiate this one with respect to x. What we get is exactly the same equation for v, d second v by dx squared plus d second v by dy squared equals 0. So first of all, an analytic function, w of z, contains 2 real solutions of the Laplace equation. That's interesting to know. Every analytic function, every function which has a derivative. And incidentally, most of the simple functions that you write down, I'll give you some examples as we go along, most of the simple functions that you would be likely to write down are analytic. So in this way, you can generate a large family of solutions of the Laplace equation. Now, it's not sufficient to have two solutions of the Laplace equation. Two solutions of the Laplace equation are just two solutions of the Laplace equation. These equations link them together. So in fact, it's not every pair of Laplace functions define an analytic function. Really, it's just one of them, and you can deduce the other one by a trick, but we don't need to go there. Okay, so that's something about these equations have a name, incidentally. They were first, to my knowledge, they were first discovered by the mathematician Cauchy, and they're called, Cauchy and Riemann. I don't know who discovered them first, Cauchy and Riemann, and they're called the Cauchy-Riemann equations.
Yeah, Cauchy was first, but sort of
But Riemann was more famous.
popularized by Riemann.
Cauchy, Riemann.
Well, isn't that often how it goes?
Yeah.
You know, somebody's
Usually the first guy doesn't get any credit, but in this case, Cauchy was a rather famous mathematician, but not as famous as Riemann,
so physicists never heard of him.
except in this context.
In math, he's got many other.
Oh, yeah, but not as much as Riemann. I don't think. Tell me something else that Cauchy did.
Cauchy sequences.
Oh, yeah. I heard of that.
He made calculus rigorous.
What's that?
Made calculus rigorous.
That you don't get credit for. Okay, the Cauchy-Riemann equations are each are related to Laplace's equation in this way. Now I want to prove that these mappings are conformal. That was the whole point here, that conformal mappings are the same as these analytic functions, mappings or coordinate transformations generated by analytic functions. They are the same thing. But let's see how we prove that. Yeah, let's just remind ourselves one small point about complex numbers. Let's suppose we have a complex number. I'll call it z. I'll call it script z here. It's meant to be a small complex number, but it doesn't need to be small, but a small complex number. But it doesn't need to be small for this purpose. It can be represented as x plus iy, but it can also be represented as another way in polar coordinates as a radius, let's call it rho, times e to the I times an angle. Okay? That's another form of a complex number. Now, supposing we have two complex numbers, let's call this delta z, because I really do mean it to be a small little displacement. Let's suppose I have another one. Let's call it capital delta z. Each one of these are intended to be small displacements, but for the moment they're just complex numbers. And this one is called rho prime, e to the I theta prime. Think about the ratio of these two. The ratio of these two, delta z over delta z, first of all has rho over rho prime. We could make it simple and set rho and rho prime to be equal. And that's because rho and rho prime are not the issue here. What I'm interested in is these angles. What do I get for the angle? I get e to the I theta minus theta prime. Okay. The important thing here is that the angle associated with a ratio is the difference of angles. If I have a ratio of two complex numbers, the angular part of it is the difference of the angles. Keep that in mind. Okay? All right, now what we're going to do is go back to the z and w planes. Here's the z plane. Here's the w plane. And let's take, starting at that point, let's construct two little intervals. One of them I'll call delta z. It's the same as this over here. Incidentally, my script z's and my square z's are the same variable. Delta z and delta z. We construct two of them here. There's an angle between them, which is the difference of the angles of the two variables themselves, or the two little intervals themselves. Now, I can map every point on this plane to a point on this plane. In particular, this point here goes to here. The endpoints also get transformed. So little delta z gets mapped to little delta w. You take the two endpoints and you map them to here, and that defines a little delta w. Same likewise with little delta z. Okay. Sorry, delta big w, delta w. Good. Now what do we know, assuming it's an analytic mapping? In other words, assuming that the Cauchy-Riemann equations are satisfied, assuming that the function w is an analytic function. What we know is that the derivative is well defined and doesn't matter which direction you come in along. What is the derivative if I come in along the delta direction? If I come in along the delta direction, it's just delta w over delta z, right? That's the derivative if I come in delta w divided by delta z. But supposing I come along this direction here, then what is the derivative?
Big delta w.
Big delta w over big delta z. Now, if w is really an analytic function, it means that this ratio doesn't depend on which direction you come in along. So it says that these two are equal. The derivative is calculated along the delta axis, or the little delta axis, or the big delta axis should be the same if they're analytic functions. We can rewrite this. Let's multiply this by big delta z and divide it by big delta w. Little delta w. We can write this in another way. It's big delta z divided by little delta z. I've multiplied. Now I'm going to divide by this one is equal to big delta w over little delta w. Everybody see what I did? I put this one upstairs and this one downstairs, that's all. But now what does this say? This says the ratio of big delta z to little delta z is the same as the ratio of big delta w to little delta w. What does that say about the angles here? Let's call that angle theta, and this angle over here. The angle associated with the ratio is the difference of angles, which just means the angle associated with the number, where is it? Delta z over little delta z is just the angle between them. The angle associated with big delta w over little delta w is the angle between here. What does this tell us? This tells us the angles are equal. In other words, the mapping is a conformal mapping. Every angle on here, when you make the mapping, maps to the same angle on here. It doesn't say it doesn't reorient. It says the angle between curves. Take any curve, map it to here, and the angle that they intersect at will be the same. That's the defining property of a conformal mapping. So the coordinate changes that are associated with analytic functions are exactly the coordinate transformations which are the invariances of Laplace equation. or the coordinate transformation, that the Laplace equation doesn't change when you do those coordinate transformations. That's why in string theory, analytic functions or coordinate or conformal mappings are so important, because they're the invariants of the equations of motion of the string. Okay, let's do a couple of examples. I'm going to show you two interesting examples. Well, let's first check a couple of simple functions and see if it's really true that let's take z equals x, w equals z squared. That's a real easy one. W equals z squared. Let's check if it's analytic. Okay. Z is x plus iy. X plus iy squared is equal to x squared minus y squared plus twice I xy. And this must be equal to u plus iv. W is equal to z squared. All right, so first of all, what is u? U is equal to x squared minus y squared. The real part of this side is the same as the real part of this side. So that's x squared minus y squared. What about v? Just 2xy.
U equals, there's a square missing in the.
Yeah, good. Right? That's what you meant, right? Okay, let's check whether these satisfy Laplace's equations. Laplace's equations say that the second derivative of u with respect to x squared, what is that? The second derivative of u with respect to x squared is 2. Second derivative. 2. Second derivative of u with respect to y squared? Minus 2. So, second of u with respect to x squared plus second derivative of y squared is 0. Okay? What about second derivative of u with respect to x squared? 0. If you differentiate it once, you get y, and then you can't differentiate it with x again. Likewise, second derivative, this one also is a good solution of Laplace's equation. All right, now, that proves that every function that you'd ever be likely to write down is analytic. Let's write one down. Let's write one down which is not analytic. Okay?
One over z.
Well, that only fails to be analytic at one lousy point, so let's not worry about that. No, let's make a really bad one. First of all, w equals z. That's very analytic. That's a very simple one. But what about w equals complex conjugate of z? W equals complex conjugate. Remember what a complex conjugate is? You reverse the sign of the I. This would say that W is equal to x minus IY, or U is equal to x, and V is equal to minus Y. I will leave it to you to prove that the Cauchy-Riemann equations don't work. I'm not going to do it. You do it. You get a wrong sign. You can see you couldn't possibly get the right sign for both plus and minus. One of them would say u equals x, v equals y, and the other says v equals x, v equals minus y. Can't both satisfy the Cauchy-Riemann equations. I'll leave it to you. I don't want to do it now. That's because I can't remember the Cauchy-Riemann equations. Oh, there they are. du by dx equals dv by dy. Nah, the minus sign gets in the way, right? So the answer is no. Okay, but analytic functions are written without ever invoking the complex conjugate. Complex conjugates are not analytic functions. W equals z, w equals z squared, w equals z cubed, w equals z to any power is an analytic function. Let's do another one for fun. Let's do w equals log, or let's do, Yeah, let me see what I was going to do. Yeah. W equals, no, Z equals e to the W. Let's do W equals e to the Z. That's a more complicated thing. Let's just check it and see that it's really analytic. You could also do logarithm. We don't have to do both logarithm and exponential. Why is that? One is the inverse of the other. If we come back, how do we know that if a function is analytic, that the inverse of it is analytic?
The angles match. The angles have to match going one way, they have to match the other way.
If the angles are preserved one way, they have to be preserved in the reverse.
Exactly. If the angles are equal going one way, they have to be equal going the other way. So it's also true that derivatives of inverse functions are just 1 over the derivatives of the functions themselves, and so if they're independent of which way you come in, it's still true. Okay, but let's try W equals, just to learn the experiment around and to unrust your use of complex numbers. All right, so W then is U plus IV, right? What is e to the z? E to the z is e to the x plus iy. All right, e to the x plus iy is the same as e to the x, which is real. E to the x is real. And what about e to the iy? Is there another way to write e to the iy? Cosine of y plus I sine of y. Cosine of y plus I sine of y. Okay, so can you read off u from this? U is equal to, let's put it up here. U is equal to e to the x times cosine y, and v is equal to e to the x times sine of y. Should we check the Cauchy-Riemann equations? Let's check them. du by dx, what is du by dx? What happens when you differentiate e to the x with respect to x? Okay, you get u again. So du by dx is same thing. Du by dx is equal to e to the x cosine y. What about dv by dy? All right, what do we get when we differentiate this with respect to y? Derivative of sine is cosine. Okay, so this is again equal to e to the x cosine y. Yep, so the first Cauchy-Riemann equation is correct, and you can check the other one, it's also correct. All right, so we check that e to the z is a good analytic function. Sums of analytic functions are analytic. Ratios of analytic functions are analytic except at points where the denominator vanishes. At points where the denominator vanishes, something is infinite, and those are nasty points where everything breaks down. Okay, let's take, I took w equals e to the z. Let's take w equals logarithm of z. That's the inverse function. W equals logarithm of z. And let's see if we can see how this mapping works. This is an important mapping in string theory. W equals logarithm of z. Let's see if we can see how it works. In particular, I'm going to apply this mapping to the half plane. The half plane now means take the half plane, which has a boundary. It's the half plane to the right. I'm not going to, let's not mark it. We're interested in the half plane to the right here. Here's the origin. And let's see if we can see, when we do the mapping, where the points of the half plane go. Here's the W plane. This is the Z plane. and here's the w plane. Okay. First of all, what about the origin of the z-plane? What happens to the origin of the z-plane? The origin of the z-plane goes to logarithm of 0. Where is logarithm of 0? Logarithm of 0 is, of course, not a number. But we can take logarithm of a tiny, tiny, tiny number, and the logarithm of a tiny number is a very negative number. So this point out here maps to some place out at infinity way off to the left here. Right? Let's not try to figure out exactly where it goes because it doesn't go anywhere really. It goes out to minus infinity. What about logarithm of plus infinity? That's way out here. Okay, but that's not very illuminating. Let's take this plane and write it in the other form. Z is equal to r e to the I theta. Then what is this half line down here? That's the line theta equals what? Theta equals minus pi over 2. Here is theta equals plus pi over 2. Here is r e to the I theta. What is the logarithm of r e to the I theta? The logarithm of r e to the I theta is log of r, log of z, is equal to logarithm of r plus I theta. Plus I theta. So where does a general point go? It goes to some real number plus I theta. And what does theta go between? Theta goes from minus pi over 2 to plus pi over 2. Here's minus pi over 2. Well, theta equals minus, is I theta is minus I pi over 2. Minus I pi over 2. And the upper end here goes to plus I pi over 2. An infinite line, in other words, this infinite line here gets mapped to this infinite line, and this the infinite half line, and the other infinite half line gets mapped down to here. The origin being way out here. So what we've done is we've taken this whole space and we've kind of bent the axes and squashed the whole space on a narrow ribbon. The ribbon between minus I pi over 2 and plus I pi over 2. Okay. We could draw some curves to see if we can see what's going on. We could first draw some straight lines like this. The straight lines coming out of the origin here. They have to go to the origin. They also have to go out to infinity. And those lines map to straight lines like this. They're just bands at constant angle. At constant angle. Okay? Next, what about the radial circles, which look like this? Where do they go? Vertical lines. Why is this strip description interesting from the point of view of string theory? This was the way I described the world sheet of a string in terms of a coordinate, what do we call it, sigma? Sigma, which went from minus pi over 2 to pi over 2. That was, if you like, the parameter along the string. And the other direction was the time direction. This was the world sheet of a string where the string went from minus pi over 2 to pi over 2 in the coordinates and swept out time. Uniformly, everything was translationally invariant in time, no special time, and you can see from this picture here that everything has a nice symmetry along this axis. How does the symmetry along this axis, let's say we push everything to the left, what happens here? On the z-plane. Let's take the W plane and shift everything to the left. What happens? It shrinks. It shrinks by a uniform factor. If you push to the left a certain amount, it shrinks by a uniform factor. If you push to the right, it expands. So these are called dilations. Dilations are transformations which expand and contract. They transform into the time translations. Curious. All right, this is one mapping which is of interest. This means that the string world sheet could be described as living on a half plane like that, with the incoming string coming in at that point, right there, being injected in right there. The incoming string at a time in the remote past can be thought of as being injected onto the world sheet right at this point. Let's do another mapping.
I have a quick question for you. So you've let R equal to be 1, is that it?
No. No, R equals 1 is some particular line here. These lines are lines of constant R. Right. R equals 1 is right at the center here. No, I did not.
Yeah, R is those circles. R is those circles that you,
Yeah, R are the various circles here. This is R equals 0, R equals 1, R equals 2, R equals 3. Sorry, R is not 0 over here, but R is 0 out there.
If I can clarify to say that the left one is like polar coordinates, but on the right it's not polar coordinates, it's the old x, y, coordinates.
Yeah, but it's a mapping from one to the other. It's a mapping from one to the other. And the one thing you can be sure of is that angles on here, when they map to here, they cross at the same angle. That means, among other things, that if the Laplace equation for x now being x of the x coordinate of the string, if the Laplace equation is satisfied for a field, for a degree of freedom living on here, it's also satisfied on here. Okay. So that's the symmetry of string theory. You can stretch, deform the coordinate space to fit whatever particular reason you may want for redrawing it. Here's another form. Another mapping of the half plane. Oh, before I do that, let me tell you what happens if you map the whole plane by the same transformation. If you map the whole plane from the same transformation, the angle goes from minus pi over 2 to what? Minus pi over 2 plus 2 pi. All right. We could also let it go, let's see, we could also let it go from, yeah, okay. It goes from minus pi over 2 to minus pi over 2 plus 2 pi. 2 pi is up, add 2 pi. And it becomes a fatter strip, but there's something new. What's new? What's different about this strip than the original strip?
It wraps around?
Yeah. Yeah. When you go all the ways around the angular direction, you come back to the same point. That means starting here, when you go all the ways around, you come back to the same thing. In other words, what happens if you map the whole plane? What do you get? Cylinder. Cylinder, not a torus, because this end is not identified with this end, but the top is identified with the bottom. You get a cylinder. Yeah, it's a cylinder, an infinite cylinder. This is the space that you would use to describe an open string with two ends. How about this one? Closed string, right. So it's natural to think of, well, open strings you can describe on the half plane, closed strings on the whole plane with no boundaries. Okay, that's useful mathematical fact. Now let's come to another mapping. Let's forget this W plane and map to another W plane. Different mapping. We're starting again with the same Z plane. X, Y, and so forth. How about this one? W equals Z plus 1 over Z minus 1. Let's see if we can see where it goes. Is that what I want? Let's see. Or do I want Z equals W plus 1 over W minus 1? One or the other. Well, let's try it. Let's see if we can see what it does. Z equals 0. Where does Z equals 0 go? Minus 1, right? When Z is equal to W, when Z is equal to 0, W goes to minus 1. Here's the W plane. W goes to minus 1. How about when Z is equal to when Z is equal to infinity, way out here.
W goes to 1.
When Z is equal to infinity, or in other words, when Z is very, very large,
Plus 1.
Goes to 1.
it goes to plus 1. How about when Z is pure imaginary up here? When it's pure imaginary, in other words, when it lies on the boundary of the half plane, where does it go? That means that Z is equal to some real number times I, R times I. What happens to W? W becomes 1 plus IR over 1 minus IR, I think with a minus sign. How about 1 plus IR over 1 minus IR? Anything special about that? Magnitude 1, right? Magnitude 1. The sums of the squares of the real and imaginary parts are the same. So the ratio of these two has magnitude 1. So where is this upper half line here? It lies on a unit circle. It lies on the unit circle because it has magnitude 1. How about the lower half line here? It also lies on the unit circle. So when X varies over the entire half plane here, not X, but when Z varies over the entire half plane, W varies over the unit disk. This is called a disk, over the unit disk. What is this useful for? Well, in practice, it is useful for solving Laplace's equation in various contexts. You put in various charges, for example, in various places, and you want to calculate the electric field. If you can do it in this geometry, then you can transform the same problem to this geometry and solve a whole slew of problems. So one of the things it's good for is mapping back and forth electrostatics problems. And it is used that way quite frequently. Let's see, let's do one other thing before we finish. Not before we finish, but before we finish with this. We started with these circles and these lines here. What do they look like on the unit disk here? Well, they look roughly like this. The radial lines start at one end and go out to infinity, but infinity was over here. So the radial lines look like this. they're actually circles. They actually are circles. Circles of different radii. And the lines of constant radius here, they look like this. And they bunch up as you get closer and closer to the... Do you remember the transformations on the ribbon here? There were transformations on the ribbon which moved, which translated the ribbon back and forth in this direction. They corresponded to dilatations or dilations, expansions and contractions here. They correspond to some complicated kind of motions here.
When you said that those arcs that you drew are circles,
Yeah.
they're circles in the,
In the W plane. They're circles, but their centers are in various places. I mean, this one is not a circle, clearly. It's a straight line, but it's the limit of a circle. This one is a circle with a center way down here. This one has its center somewhere here. This one has its center somewhere here. And of course, this one has its center right over here. So,
Would cartographers like that transformation? It kind of looks like,
well, of course, that's not a sphere. It's a disk. Yeah, don't confuse it with a sphere. Now, if you did the same thing with the full plane, you would get a sphere. But I didn't want to do that now.
the optical illusion anyway, that those are
Yeah.
big circles on a sphere.
Yeah, it looks like a sphere, but it's not intended to be a sphere. It's just intended to be a mapping from the plane to the disk. All right, so we have now another representation of the same picture. The left half plane goes to the outside of the disk. Left half plane, right half plane is here. That's the inside of the disk. The left half plane goes to the outside of the disk. It didn't disappear. It just went to the outside of the disk. I don't know who asked the question.
It's a sphere because when you take the limits, things go around and they
In which
fold up, right?
You mean when you take the full plane? The full plane, it's a little bit complicated. It's a stereographic mapping of a sphere.
I think there's a single point at infinity and there's a mapping directly.
Yeah. And it can be mapped stereographically.
Which was the radials? The radials on the left, the spokes going out, which set of curves did they go to on the right?
The spokes going out here, they begin at this point. This point is that point. Infinity, let's see, z equals infinity, that's w equals 1. That's over here. So every one of these lines, let's take the one which is, first of all, completely symmetric between the upper half plane and the lower half plane. That's the x-axis. The x-axis, that's just this line. Okay? The radial lines above the axis, above the x-axis, are like that. Radial lines below the x-axis are like that. Okay? Then there's the circles on here. Here's a circle. Every one of these circles sort of surrounds this point here, sort of, half surrounds it. They start, well, let's see, they start on the boundary, they surround this point, and they come back to the boundary. So they start on the boundary of the disk, they go around, and they come back. But as you move out, you go like that. They sort of get turned a little bit inside out as you go from here to here so that their curvature is in the opposite direction. Yeah, they are also circles. It's an interesting fact. Under these mappings, under this mapping, under this kind of mapping, this is called a linear fractional mapping. It's linear. It's a fraction made out of two linear functions. Under linear fractional mappings, the collection of circles and lines transform into the collection of circles and lines. So here's a line, it transforms to a circle. Here's a line, it transformed to a certain circle. Circles and lines transform, the collection of circles plus lines transform to circles plus lines. Not under every conformal mapping, under linear fractional transformations, and that's what these are called. Sometimes called Möbius transformations, and they have nothing to do with Möbius strips. At least I don't think they do. Same Möbius, though. Okay, let's take a break for 5 minutes or so.
What about that point at halfway infinity?
The point where?
The point at halfway infinity is a straight line
The point at halfway infinity. What is a halfway
on the
infinity?
basketball.
What is halfway infinity?
Isn't that straight line in the vertical line in the middle there?
That one. Yeah. That's some particular radius. Probably radius 1. I'm not sure. Let's see. It goes through the point. It goes through the origin. Yeah. It passes through the origin on the W plane. So where is the origin on the W plane? It's the thing whose logarithm is 0, 1. Right. Now I'm going to try to give you a fairly complete definition of what string theory is. We've set up a lot of the mathematics. The problem, of course, is proving that these things work in detail, and that, of course, is where the real difficult stuff comes in. But let's go back. You may recall that we talked a little bit about what scattering amplitudes look like and how you derive them in string theory. We started with a simple example where 2 particles collided, came in, and 2 particles went out. We said, okay, let's just take the world sheet of the whole process to be a infinite strip like this. But since 2 particles are coming in, let's slit it down the middle like that. 2 particles are going to go out. Time goes from left to right. 2 strings come in. 2 strings go out. So here's the 2 initial strings. I don't want to draw on this, at least not with black. Here's the incoming string, and it propagates. Here's the other incoming string, and it propagates. The 2 strings join, form a single string. Here it is in here. And then after a period of time, how much time? The answer is you integrate over the time. As in quantum mechanics, you always integrate over all possible paths from beginning to end. In other words, you sum up the amplitudes for all possible histories, and then in the end, what goes out is 2 strings again. What do you calculate? I'll remind you what you calculate. Well, we talked about it in several different versions, but in one version, you think of a path integral. In the path integral, the degrees of freedom are the coordinate positions. We could define a sigma variable and a tau variable, or 2 coordinates on this, 2 coordinates on this world sheet, but the degrees of freedom are the space-time positions, the space-time coordinates of a point on the world sheet. So what are they? They're x mu, where mu goes from 1 or from 0, 0 being time. What's the last one? 25 if it's in 26 dimensions, 9 if it's in 10 dimensions. But whatever the collection of coordinates are that describe the location of a point on the string, and we call that x mu of sigma and tau, let's say. Sigma and tau could be the 2 coordinates on this world sheet. They're, of course, the same as these little x's and y's here. They're the coordinates in a two-dimensional space, and those the sigma and tau are. The x's are coordinates in real space-time. The sigma and taus are just labels which label points on the world sheet. The x's are their real space-time location. And if I know the space-time location of every point on the world sheet, then I know how the world sheet is spread out over space. What do? We calculate a certain path integral. And the path integral that we calculate is e to the minus the action. We did a little trick. I'm just reminding you now of a trick. We did a little trick of letting tau go to I tau in order to get rid of various factors of I. We talked about it. I'm not going to do it over again. And there was an action. The action was the integral over d sigma and d tau of what? It was the x mu d tau squared minus the x mu d sigma squared, plus the x mu d sigma squared. What exactly does this mean? The x mu by d tau squared means the sum of 26 terms. The x1 by d tau squared, the x2 by d tau squared, the x3 up to the last one. That's what these things mean. This is the exponential of the action. And what do we do with it? We integrate it, path integral, over all possible ways of filling up the surface. It's often written delta x of sigma and tau. This means path integral, and it means integrate it or sum it up over all possible configurations of the world sheet in space-time, the way the world sheet fills up space-time. But how does this formula here, first of all, how does this formula know about the momenta of the incoming particles? The momenta of the incoming particles we have to add in by hand. And it's inconvenient in this picture to say how we do it. I'm going to tell you in another picture exactly how we do it. But for the moment, let's just suppose somehow we have put in the momenta of the incoming and outgoing particles. They're somehow embedded in this calculation. And we integrate over all x's. Now, there's one more thing. What about the time interval between here and here? We integrate over it. All right, so what we're doing, in effect, is summing up all possible ways, all possible histories of these two particles oscillating, then forming a single particle, and then forming two particles again, all possible histories, all possible ways that the world sheet fluctuates. That's this integral over here. It's an integral of the action, and it's a complicated thing. And we haven't even yet put in the rule. I'm going to tell you what the rule is for the external particles in a moment. But before we do it, what did we call this? We had a name for this picture. What was it? The sports Band-Aid. Yeah, the sports Band-Aid, right. Butterfly bandage or whatever it's called, right. Well, now we can make use of our freedom to map this picture to other sets of coordinates for the world sheet. Conformal mappings. Conformal mappings is a very wide variety of analytic functions, and in fact the variety is so large that you can basically map. This thing has one boundary. The boundary goes from here to here. Now, out at infinity here, what goes on at infinity is subtle, but let's jump to this boundary. It goes all the ways around, just like the sports bandage goes around once. It has one boundary. Apart from the fact that little pieces of the boundary are off at infinity, we'll worry about that later. You can map anything with one boundary like that to anything else with one boundary by a conformal mapping. In particular, if you so choose, just for symmetry, you can map this whole world sheet to a circle or to a disk. Exactly the same disk. I showed you how to map a single strip to a disk. I didn't show you how to map the sports Band-Aid to a disk. It's a little more complicated. I once figured it out. Many years ago, I worked out the mapping in detail. I don't remember it. But you can map it to a disk. And then where are the incoming particles? Those are points on the boundary. The outgoing particles are also points on the boundary. Let's draw some lines to just indicate how this looks. So we can draw some vertical lines here, some vertical lines here. They will look like this. Notice that these vertical lines over here surround the point at infinity here. That's this one. And then all of a sudden, they come together like that. That's this point. Then they go like this. That's what the mapping from here to here looks like. The horizontal lines, I don't know, they're a little more complicated. That's what it looks like. The point is, you can do you don't need to know where these lines are, incidentally. You can forget where they are. They don't play any special role. The point where they split and join in this diagram here is determined by the positions of these external points here. As you move them around, these points move closer and farther apart. When you move these points together this way, these points get very far apart. When you move them together horizontally, these points move together. So the same picture, the same physics, different pictures. What do you do here? You do exactly the same thing. You take dx by d tau squared. You could now call it. You could now call these coordinates by different names if you like. You could call them x and y or u and v. Doesn't matter. The tau and sigma coordinates. You calculate exactly the same quantity, integrate it over here. But now I can tell you what you do with the external particles. You have a rule for each external particle. One more factor in the integrand. Anybody know what that factor is? It's the thing which injects momentum. Delta function of what? Okay. X's are integration variables. K's are the momenta. K1, K2, K3, K4. These are the momenta coming in and going out. You put in for each external particle, each particle coming in, you put in a factor into the integrand here of e to the I k x at the position, let's call this point Z, a product for each external particle. One more thing goes in. It's a factor of e to the I kx, where k is the momentum of the particular particle that's coming in. So you have an e to the I kx1, and they're on the boundary. They correspond to particles being injected into the diagram like that. That rule comes from quantum mechanics. It comes from, well, we can discuss this rule another time. I wanted to lay out the whole set of rules. You do a path integral over all possible embeddings of the world sheet into space-time, all possible ways that this world sheet can be embedded in space-time, e to an action, and for each external particle, an e to the I kx, where the x is at the point where the insertion of that particle happened on the world sheet here. Z here corresponds to the coordinates of this point on the plane here. One last thing, after you're finished, you have to integrate over the positions of these insertions. That's it. That's the whole story. That is what string theory is. This is open string theory. That's the whole set of rules, a path integral over all world sheets, all embeddings. You can describe it on a disk, you can describe it on a sports bandage, you could describe it however you like.
What did you get after you finished all this integration?
The scattering amplitude. The scattering amplitude for a particle of momentum k1, k2, to become k3 and k4.
But if those are fixed, how come we integrated over them?
The momenta or the positions?
Momentum.
The momenta, no, we didn't integrate over the momenta. We integrate over the locations on the disk here
Of those,
of the insertions.
okay, so those don't represent the actual values, they just represent where they are. Those point,
They replace the integration over the separation here.
right, okay, so that doesn't, so those are fixed, those are
Those
balanced.
are not fixed.
No, I
now-
mean the K1, 2, 3, 4
The
are,
Ks are fixed. The Ks are the momenta of the particles coming in and going out.
so we get basically the scattering amplitude, right?
Scattering amplitude for a particle of momentum 1 and 2 to become a particle of momentum minus k3 and minus k4. Remember, all momenta are in.
Is that product multiplied by the whole integral?
It's inside the integration.
Inside the...
Inside the
Is
integration.
that, you call that the action?
This is the action.
And that's part of the action?
These are called vertex operators. The vertex operators mean they just they just deposit momentum into the diagram. They inject the flow of momentum into the diagram. We'll work that out another time and see where
The
this comes
question
from.
is, do they go inside the upper integral?
Yeah, they go inside the integrals. Not inside this integral. No, not inside that integral. No, we could write it out. Let's write it out more clearly. Integral over all possible, well, let's see, integral, path integral. Let's just call it path integral. Let's not put any d's there. E to the minus the action. E to the minus the action. This is the action for a particular configuration, and here it is. This is the action, times for each external particle, a factor e to the I k x of z1, let's say zi, ki, a factor for each one, k1, z1, yeah, well, let me not put it for a moment. E to the I k2 x of z2 dot 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 for each external particle, where z's are the positions on the disk where the momentum is injected. This is path integrated and then integrated over the locations where the momenta are injected. Okay, so you integrate over everything, yeah.
And you use the IKX, even though we've already done the Wick rotation?
Yeah, still e to the ikx, right. That I is a different I. You should really write k mu x mu, k mu x mu. Okay, there's a k mu for each component of momentum and an x mu. There are 26 x's, there are 26 k's, and that's it. That's the whole structure of string theory.
Question,
Okay.
the momentum is a vector, right?
K mu, that's why there's a mu there.
Okay, and then the direction is related to the x sub z's?
No, the direction of the momentum is here are the components of the momenta. Here are the components of the momenta. The x's which appear there get integrated over. They're part of this path integral here. integral delta x. Yeah. They could be, since they're in the exponent, you could consider them to be part of the action if you liked. You can just put them into the action, but you add them in a kx for each external particle.
So how does this, when you have the bandage, you know, the legs can be either splayed or closed. Does that relate to the x's, how that's mapped?
The shape of the bandage, how?
The angle of the two legs.
The angle, no. In this drawing, you just draw them horizontal. You can draw it any way you want. Right, it's not in real space. Right, it's not in real space. It's just a parameter space that'll, right. Okay. The amazing thing is that you can do the integrals. Everything can be done. These are what are called Gaussian integrals. Everything is quadratic in the exponent. All the integrals can be done. That's the good news. The bad news is you almost always get infinity. But not if you're in the right number of dimensions. Now, I am not going to tell you about the wrong number of dimensions. I'm going to tell you what the answer is like in the right number of dimensions, and it's incredibly simple. It's the solution of an electrostatics problem. It's the solution of an electrostatics problem. You take every one of these x's and think of it as an electrostatic potential. There are 26 of them, or 10 of them, or however many of them there are. Think of them as separate electrostatics problems. It's a world now where there are 26 different kinds of electric charge, 26 different kinds of electric field, and 26 different kinds of electrostatic potentials. The electrostatic potentials are these x's, x1, x2, x3, x4. What do you think the charges corresponding to them are? Can you guess? The components of the momenta.
In 26 components?
The 26 components of the momenta are like 26 kinds of charges, each one being the source of its own electrostatic field, the electrostatic field being called x. Okay, here's the calculation that you do, and it is really easy. It is obtained by doing these integrals. The integrals, 26, not 26 charges, but 26 different kinds of charge. Right. 26 different independent kinds of charge, each creating its own electrostatic field. All right. Here's what you do. You take a disk. This disk is, think of it as a world in 2 dimensions. On this disk, you have, let's see, I get confused, the x, yeah. The boundary conditions are that the components of the electric field perpendicular to the surface of the disk vanish. It's not so important, the boundary conditions. You have a disk, a world with these 26 different kinds of electricity. On the boundary, you put charges. Little charges on the boundary. At each boundary point, there are 26 charges to put on. The charges themselves are the components of the electrostatic potential, the components of the momentum. So if this particle comes in with 26 components of K, those 26 components of K become the 26 charges that you put at that point, another 26 charges at that point, another 26 charges at that point, and another 26 charges at that point. This is a straightforward electrostatics problem, 26 of them, but it's as easy to do 26 of them as it is to do one of them. Well, in principle. If you can do an electrostatics problem with one kind of electric charge, you can do the same electrostatics problem 26 times over with different values of the charge here. All right, so fixing the values of the charge and fixing these points. What do you calculate? You calculate the electrostatic potential inside. From that, you can calculate the electric field. And once you know the electric field, you can calculate the electrostatic energy. You calculate the electrostatic energy of such a configuration. That's this whole integral there, the electrostatic energy, and then you integrate it over the points. You move the points around, you integrate over them, and that is the scattering amplitude for the 26-dimensional particles to scatter from one set of momenta to another set of momenta. So in fact, the final upshot is very easy. It's just an electrostatics problem with 26 different kinds of charges. You calculate the electrostatic energy in here.
Is that one energy or 26 energy?
26. There are 26 and you add them up. That's right. There are 26 distinct,
You have 26 potentials,
26 electric fields.
and you end up ultimately with one energy, right?
One energy. One energy.
And there's no cross terms between the 26. The 26 are just operating orthogonally.
There are no cross terms between them. You take that electrostatic energy, you exponentiate it, e to the minus the electrostatic energy. The whole answer depends on the positions of the charges, and you integrate it over the positions of the charges. Okay? You calculate the 26 electrostatic energies for the 26 different kinds of charges. How do you do that? You calculate the electric field, you square the electric field, or you can just calculate the electrostatic energies if you're, and you exponentiate it, you integrate it over the positions, and that gives you the scattering amplitude for particles whose components of momenta are the same as the values of the charges that you put on these points. That's the whole upshot of it, yeah.
The angular parameter of this disk has no relation to scattering angle, right?
No, no. No, it has more of a relationship to the time intervals in here. Yeah. There are various parameters, but you integrate over them. You integrate over them, and that's the string theory scattering amplitude. It's a fairly simple prescription.
Could you say this does not work if it's not 26?
Doesn't. You get a bunch of infinities from the path integral which just don't go away. This is the final answer when it works. When it doesn't work, it's just infinite. And 26 and 10. So I'm sort of short-circuiting it by telling you what the answer is. It's a very beautiful and simple final answer. But once you know that this is the procedure, there's nothing to prevent you from putting lots more particles in. You do have to integrate over their locations on here, but basically that's the answer for the scattering of any number of incoming particles, the amplitude, the thing that you square, the amplitude for any number of incoming particles to any number of outgoing particles. Yeah.
We have three long dimensions and these small ones. So the fact that you convert them to this.
Whoa, 3 long dimensions. Well, we haven't talked about compactification yet. We have not, and that'll be the next discussion. Yeah.
I'm just trying to think about that connection to the potential again. It's because of the coordinates satisfying the Laplace.
Yes, it's because the coordinates satisfy the Laplace equation, and
Connects you to the static
That's right.
potential solution.
that's right. The coordinates satisfy, well, yes, they satisfy the Laplace equation, and the Laplace equation is the basic equation for electrostatics. We didn't have to call it electrostatics. I could have just said Laplace equation with some delta function sources here. But the mathematics is the same as calculating an electrostatics problem.
You have 4 degrees of freedom for each of
those 4 points around the disk, right? Each angle has an angle, and then you have...
Yeah, it's actually simpler than that. You can use the conformal freedom, the freedom to reconformally map things, to arbitrarily fix the location of any 3 of them. In other words, you should integrate over all of them, but for any given configuration, you can always find a conformal mapping which will bring this point to here, this point to here, this point to here, and then it's only the 4th point. For the case of 2 in and 2 out, it's only the location of the 4th point which gets integrated from here to here. That's a technical point.
Place the 2 points inside the band,
These 2 points, yeah. The integral over these two,
freedom there, right?
no, there's really only one integration, which is the time between these two.
They don't have to exactly break apart in the same.
That's a good point. They could break apart at different points, like that. But you can always find a conformal mapping which will pull them back together. So you have that freedom. You have that freedom to pull them back together.
So when you add more points, how does the number of points map to the number of parameters?
Well, the answer is that you have a conformal invariance freedom, a freedom of conformal mapping that allows you to choose any arbitrary 3 points and put them wherever you like. You fix them, put the first one here, the second one here, the third one here, and then all the other ones get integrated over. So the answer is you have n minus 3 integrations to do. Yeah, n minus 3 integrations to do.
How does this procedure relate to M theory?
To what?
To M theory.
Doesn't yet, not yet. We'll hopefully come to it.
The other diagram that you had where you had the squiggly line going vertical. In other words, you had the 2 particles coming in. That would correspond to if those 2 points were actually, if you had a negative.
You want to study it if you use a coordinates in which it looks like this.
And then the other one reaches all of it. No, further, the top one goes further to the left, past the...
Then the integration, you can pick one of these. You can hold one of them fixed. The other one has to go all the ways to, from plus infinity to minus infinity.
I was just comparing to the path, the 2 paths that you had that you said were equivalent. That would be equivalent to, say, the top break, the point at the top break being to the left of the point at the bottom break.
Yeah. Yep, you do have to do that. You have to integrate over. But in the special case where you have them at exactly the same height, the integral terminates when they touch. And it's the same integral. The amazing thing is it's the same integral. And in fact, it's the same integral as integrating over the points on the boundary of a disk. So this is a sort of nice, uniform, symmetric picture in which all the particles are on the same footing. And you can pull it and you can, pull it out and push it in various ways to make it look like different kinds of processes. But
it's nice.
Yeah. So this is open string theory. Open string theory, the particles are injected on the boundaries. The boundaries, and these are the edges of the strings, the endpoints of the strings. That's what the boundaries are. We'll talk about closed string theory a little bit next time. So you can see the mathematics of it at this level is fairly simple. Well, it is. I mean, it's just electrostatics.
When you say this is basically string theory, is this model, this matches up with experimental results? So when using this formalism, you match what you get when you run the experiments?
Which experiment are you thinking of?
Colliding particles.
It's a reasonable description of hadrons. Nobody has the vaguest idea what happens when you collide gravitons together. So, we have a good idea. We have lots of idea. But the details of it are way beyond us. And there is a zillion versions of this. Don't get, this is, I have described one simple version of a string theory. There's a zillion versions, and the zillion versions are connected with the way the extra dimensions are compactified. We haven't talked about that. No, this doesn't agree at all with experiment. It has 26 dimensions of space. How could it compare with experiment? It's terrible.
At the other end, that when you talk about these scattering amplitudes, you're talking about something that is, they're not things that you can measure in any experiment. What I'm trying to figure out is you're calculating a scattering amplitude.
Right. And you're asking whether it agrees with experiment. The first thing you would discover if you took these scattering amplitudes and compared them with experiment is the number of dimensions was radically wrong. Immediately. You can't even get started with it. I mean, we have a lot more to do before we could make a sensible theory out of this.
Details.
What could be worse? The number of dimensions of space is, there's 25 of them instead of 3. It's, it's off by not even an integer. Oh, it's better in superstring theory. There the number of dimensions is 9, and it's only 3 times too large.
I just wanted to get clear that this was pure mathematics.
At the moment.
So does that mean that eventually we'll come around to a point where you will compactify these things and then get reasonable numbers that we see somewhere on something?
Yeah, but the real complexity and enormous difficulty of this subject, the mathematical sophistication of it, is in the compactifications. And it is really hard. It's where the difficulties are. And I can show you some simple examples of compactification, and I can show you how they lead to information about particles and about gauge groups and things like that. But to do the real thing is far, far, not only beyond me, but it's far, far beyond the subject. I mean, nobody knows how to put these things together to make realistic theories of particles. This is a machine for making lots and lots and lots of different models. The number of models or the number of constructions that can be made are in the 10 to the thousands. So this is very much a work in progress. But on the other hand, there is a very, very definite mathematical subject of constructing such models. They are highly rigorous, and they produce an enormous wealth of mathematical information about gravity, about mathematics. But there's no question that it has not succeeded in giving a theory of elementary particles, or better yet, it has succeeded in giving about 10 to the 500 theories of elementary particles, which is, it may be like that. I think it's like that. But we will find out. This is, I am not proselytizing for this theory. I'm simply telling you what it is.
Is there a brief description for how we came about with 26 dimensions in this model, or?
Yeah, there's a brief description, and unless we talked about it. We talked about 1 plus 2 plus 3 plus 4 equals minus a 12th, and 12 times 2 is 24, and 24 plus 2 is 26. Remember that?
Yeah. Are these K's quantized in any sense?
Are they what?
Are they quantized, or are they considered continuous value?
Which, the K, the momenta? Which things?
When you look at the electrostatics, do you assume that there's a quantization, or do you assume that it's a continuous value?
No, the only thing that's quantized is the sums of the squares of the momenta, which is the mass squared of the particle. No, momenta is not quantized, most definitely not. Okay, good.
For more, please visit us at stanford.edu.